Thanks very much. Thanks for the opportunity to speak here. I will speak about joint work with Mengdi Wang, who is currently a postdoc with me in Stockholm. And this talk will be about linear equations and smooth numbers. More precisely, it will be about an investigation into whether Green and Tau's nilpotent Hardy-Littlewood method can be applied in very sparse multiplicative settings. I will start by giving a very brief overview of what this nilpotent Hardy-Littlewood method can do before moving on to describing the sparse multiplicative setting I want to test the method in. So to start with, the nilpotent Hardy-Littlewood method can be used in order to asymptotically evaluate correlations of arithmetic functions. The type of correlations that you can study with this method requires the following input data. You need a system of linear forms. These will be linear forms with integer coefficients and at least two variables. And you need to assume that they are pairwise linearly independent over the rational numbers. You may shift each linear form by some constant, these a's here, so as to obtain a linear polynomial. And then we want to study correlations between arithmetic functions, and the arithmetic functions here are denoted h1 up to hr. The correlations we will look at take the shape star, where you evaluate each of your arithmetic function at one of the linear forms shifted by one of the constants. And this product is summed over lattice points in some nice region. K is some fixed bounded convex set of positive volume and R to the S. And this set we take and we dilate it by some parameter n. And now we would like to know what happens to these expressions asymptotically as the dilation parameter n tends to infinity. The methods can help you asymptotically evaluate such expressions, provided the arithmetic functions you're working with satisfy two conditions. On the one hand, you need to be able to find a family of pseudo-random majorizing functions for your arithmetic functions. I will say more about what pseudo-random means a bit later. These majorants are used in order to transfer the problem of evaluating these expressions here to a similar problem where the functions, the arithmetic functions, are all bounded. That's one requirement. The other requirement is the following. If you take any one of these functions, h1 up to hr, restricted just to the integers up to capital N, then you have a function on finitely many integers, and you can compute its mean value on these finitely many integers. I will denote that mean value, which depends on n, by mu j, and consider on those first n integers this centralized function hj minus mu j that has now mean value 0 on the first n integers. And beyond having mean value 0 on these first n integers, we also need to know that these centralized functions are small and all uniformity norms of sufficiently large order k. By the inverse theorem for uniformity norms, which is a result due to Green, Tau, and Ziegler, we know that in order to obtain this condition here, it suffices to show that these centralized functions are orthogonal to certain objects called nil sequences. So null sequences, this null sequences part is where the nilpotent part of the name of the method comes from, I believe. These two tasks are what are needed to resolve in order to apply the method to find asymptotics for such expressions. And now I would like to move on and say a little bit about the sparse setting in which I would like to try these methods. So an integer n is called y smooth if all of its prime factors are bounded above by y. That means if its largest prime factor, denoted here by p plus of n, is less than or equal to y. We denote by s of y the set of y smooth numbers. And for any cutoff parameter x, we denote by s of x, comma y, the subset inside the interval of integers between 1 and x. Psi will denote the cardinality of the set. And now I will distinguish three settings. It's not quite standard what is written here. If your smoothness parameter y is of the form x to the epsilon for some fixed real number epsilon between 0 and 1, then the y smooth numbers up to x form a subset of the integers up to x that is that has positive density. So that's the dense set. When you replace the exponent epsilon by anything that tends to 0 as x tends to infinity, then you obtain a sparse subset of the integers 1 up to x. And there is an asymptotic formula here that is valid provided the smoothness parameter is not too small. When you are at the lower end of this range, so if you choose a y that has the shape log x to some power k, which is larger than 1, the density of these y smooth numbers up to x will be a negative power of x. So that is an extremely sparse set when compared, for instance, to the set of primes. Now the question I would, the overarching question I would like to address is the following. We would like to understand for what values of y, for values of y that are as small as possible in terms of the cutoff parameter n, for which of such y we can prove non-trivial lower bounds for the frequency with which a given system of linear polynomials with the property that the linear forms that are involved are pairwise linearly independent. So I would like to understand if I can get non-trivial lower bounds on the frequency with which this system of linear polynomials takes y smooth values as the variables are bounded above by something in terms of n. That's the overarching goal. Why is this interesting? It is known that smooth numbers in general cannot be sieved. And in most applications we've seen so far of the Green-Tau methods, sieve entered in the process of producing majorizing functions. So it is interesting to understand if we can still apply these methods in situations where sieve methods are no longer available. What is known about this question? Well, we definitely have results in the dense case. There are results by Lachon, who uses the Green-Tau methods to study this question star in the dense case. There is some other work by Barlow, Bloma, Matthiesen, and Tenenbaum who have a different focus. So this result here is a special case of the result. There's lots of work on smooth numbers, on studying smooth values of polynomials, most of it restricted to the dense case. There's some work on smooth values of binary forms, some going beyond the dense case. But if you restrict to questions of this shape star, I think this is the previous work. And there is previous work in the case where this product here has just 3 factors, and to that work I will return in a bit. And you look at this question here, you may note that the characteristic function of y smooth numbers is a multiplicative function. And a second reason for which I thought this question was interesting is that it's possible to asymptotically evaluate these expressions here when you replace the characteristic function of y smooth numbers with a sequence of multiplicative function of h1 up to hr and quite some generality. However, the properties that these multiplicative functions have to satisfy include this condition here, that if you consider your multiplicative function along the sequence of primes, evaluate them in absolute value and sum them with a logarithmic weight, then you will need your multiplicative functions to exhibit some density along the sequence of primes. And this density assumption here prevents you from applying previous work in the multiplicative setting to the case where you have a characteristic function of smooth numbers in the sparse situation. So I thought it would be interesting to understand if the methods can be extended to a sparser situation. Now let's think about how small the value y here can possibly be. And in order to find out how small we can choose y, I would first of all like to mention that if the Green-Tarr methods apply in order to asymptotically evaluate such expressions, then the answer you will get from the methods corresponds to what is the expected number of solutions in this problem. Why is that so? Because if you apply the methods, you will take this expression here, you will replace any factor that occurs in here by the factor minus its mean value and add in the mean value again. So you will consider, instead of this product over functions hi evaluated at linear polynomials, you take hi minus the mean value and add that in again. And if you multiply out that expression, you will pick up one contribution from all those mean values, and all other factors that occur when multiplying out they contain one of these centralized functions. And provided all the prerequisites of the methods apply, all those additional factors contribute to the error term. So in that sense, the Green-Tarr methods, if they apply, will provide you an answer that gives you an expected number of solutions. In this talk, I will omit W tricks completely. So what you usually do is you work with a W trick and you will be able to, instead of getting this product of mean values, get something where a product of local factors occurs that takes into account any obstructions to solubility modulo small primes. So that will be ignored in this talk. However, we will get the expected number of solutions. Now, I had mentioned that beyond the work in the dense situation, there is work in the situation, there is previous work in the situation where the number of factors in the product is equal to 3. And this work corresponds to solving the equation a plus b is equal to c inside the set of smooth numbers. This equation can be phrased in the shape of one of our linear correlations by looking at how often this product of 3 factors n1, n2, and n1 plus n2 takes values in the set of y smooth numbers. This is a question that has been studied by Lagarius and Soundarajan in 2 papers, one in 2011, one in 2012. And in the 2012 paper, they show, assuming GRH, that the counting object here has at least the expected number of solutions. What would be the expected number of solutions? Well, you have the number of y smooth integers below capital N choices for n1. Similarly, you have, that gives you one of these psi factors. You have the number of y smooth integers up to n for little n2. And then the sum, this third factor, if your set was randomly distributed, will be a y smooth number with probability given by the number of y smooth numbers up to n divided by n. And that gives you what is here on the right-hand side, except this logarithmic term there should have been a y. This result applies provided the smoothness parameter is at least as large as power of log n, and the power is something larger than 8. The GRH restriction has been removed in later work by Harper, and he almost obtains Lagarius and Sandra-Jones result without this condition, but he needs the exponent to be a little bit larger. On the other hand, if y is quite a bit smaller than this, so if you use a y of the shape a power of log n, where the exponent is less than 1, then the ABC conjecture implies that this counting function here only has a bounded number of solutions. In conclusion, if we hope to apply the Green Tower method in order to study generalizations of this object, the best we can hope for is that y is as small as some fixed power of log n where the exponent is sufficiently large. That is the limit of what we can hope for. Now, if we would like to apply the methods, what do we need? Well, first of all, we need arithmetic functions that we can apply the methods to. And it might not work that we can just put in the characteristic function of smooth numbers. So what we are looking for are weight functions.
Sorry, there's a case k equal 1, which is like the transition.
Yes.
Kappa. Single itself out in your discussion. That's where the transition is from.
Yes, what I will discuss will have an exponent that is sufficiently large, and I think my exponents will be larger than.
And so you'll never get down to the super sparse case.
No, I will not get down to the super sparse case, and
Right.
there will be some further restrictions coming later. So that's a challenge for people. So we might not.
When you're close to ABC, it's probably.
Right, I mean, then it's just a diaphantom.
Yeah, it's a diaphantom.
Solutions generically.
Yeah, but if you have you applied your methods, maybe at the end, let's talk about application.
Okay, so we might not be able to apply the methods with the characteristic function of y smooth numbers. So we are going to look for a weight function g. There will be one weight for each cutoff parameter n. So we are looking for a function defined on the first capital N, n integers with support in the y smooth numbers below n. We will try to normalize this to have mean value 1, and we need to ensure that if you centralize your function, then it is small and all uniformity norms to sufficiently high order k. That's one thing we will need in order to apply the methods. The other thing we need is a majorizing function, 1 for each parameter n. These will be pointwise majorants with some implied constant. And these majorants should be pseudo-random, which in this case means they should satisfy the so-called linear forms condition. And there are many ways of phrasing this condition. I will put it like this. We will need majorizing functions for which this type of correlations is possible to evaluate asymptotically. These are the same kind of correlations we would like to evaluate for our weight functions g. But for our majorant, we must be able to evaluate them for a significantly larger number of factors, and we must be able to evaluate them for a significantly larger number of variables. In conclusion, the majorant function needs to be much easier to understand than the function g, this arithmetic function we would like to study with the methods. These are the two parts that need to be resolved in order to apply the methods. I will focus on this talk on this first part, the second part being work in progress. And for this first part, we obtain the following result. What is written on the slide is not completely correct because I will omit this W trick all the way through. So the statement is not quite correct as written, but it will make the notation significantly easier. So we will show that for any sufficiently large n, and for every smoothness parameter that lies between some fixed power of log n that is sufficiently large and a small power of n, we will show that there exists some weight function g with support in the y-smooth numbers, which is normalized to have mean value 1, and which has the property that it is orthogonal to all polynomial sequences. I don't want to define what sequences are in this talk. If you haven't seen these objects before, you may think of the new manifold that appears here as R modulo Z. You may think of the Lipschitz function that appears here as the function e to the 2 pi I m. And you may think of the polynomial sequence that occurs as a polynomial with coefficients in the real numbers. And in this situation, in this example here, you are in a more classical situation. You are studying the correlation of an arithmetic function with some exponentials with linear polynomial faces. In particular, you may study your arithmetic function twisted with exponentials with linear faces. And in this case, there is previous work by Adam Harper, who proves that provided y lives between power of log n and a small power of n, and provided theta and a certain precise y is a minor arc sequence, then the characteristic function of y-smooth numbers is orthogonal to such exponentials with minor arc frequencies. Harper's statement is much more precise than this. If you have been working with sequences before, then you may know that one sometimes can take a proof which is written in this classical setting and translate it to a proof in a sequences setting. That's not the case here, because Harper's proof relies on cancellation in while sums, which are much stronger than what we will be able to arrange for in a sequences setting. So this proof cannot be translated. Nonetheless, our result here, as will become later, indirectly depends on Harper's result. Okay, so when you go back to this special case where you are allowed to use exponentials with, say, linear phase functions instead of these general sequences.
So the problem is that the equidistribution bounds for nil sequences are not good enough. When you said before that the cancellation in fail sums, and
so in here when you sum the exponential sum bounds you get in the proof are extremely strong, and they are stronger than what we can arrange for in the proof.
we don't know, or because it's not true?
I think because of the bounds we are able to prove, and I will explain this in a slide or two. I will return to this problem. So if you consider the special case of these correlations, when you have the linear phase functions involved, then in particular, you can say something about the distribution of G in arithmetic progressions, because you can encode your arithmetic progression using additive characters. So if you would like to prove such a result, then the minimum requirement that the function G has to satisfy is that it is equidistributed in arithmetic progressions. And this will be the starting point for our search for a suitable weight function. As a minimum requirement, our function needs to be equidistributed in arithmetic progressions, and for technical reasons, it should be equidistributed in short arithmetic progressions. And with this in mind, we will start by looking at what is known about the distribution of smooth numbers in arithmetic progressions. That's a question that has been studied by many people, and I think the latest result is due to Harper, who improves work of Sandra Rajan. Harper shows that if you count the number of y-smooth numbers up to x in an arithmetic progression A modulo Q, where A is coprime to Q, then this counting object you have here is asymptotically equal to 1 divided by the number of progressions you can choose here, times the number of y smooth numbers up to x, which in addition are co-prime to the modulus q. This result tells us that smooth numbers are equidistributed in residue classes and reduced residue classes to a fixed modulus q. However, the appearance of this restriction to just numbers that are co-prime to q destroys the kind of equidistribution properties that we need in order to apply the methods. It's not the equidistribution that we need in order to continue. And for that reason, we will change the set of numbers we are looking at, and we will restrict to a subset of smooth numbers that are also free from small prime factors. So we introduce for any y prime that is smaller than y, the set of y smooth numbers, all of whose prime factors live in this interval here. And why do we do that? So for these numbers, we introduce some notation and analogy to previous notation. We denote by psi of x, comma, the interval, the cardinality of the set of our subset of y smooth numbers restricted to the interval between 1 and x. And there is some notation for the count restricted to integers below x and restricted to a progression a mod q. Why do we do this? Well, if you restrict this count here to integers that are free from prime factors less than y prime, and if you consider a q that is smaller than y prime, then everything you count here on the left-hand side will be co-prime to q. And the hope is that then on the right-hand side, the restriction mod q here is no longer causing any problems. And that's precisely what you can do. So Harper's result is written once again here. And we show that in the situation where you remove small prime factors, you obtain an asymptotic result where when you count in the progression a mod q, this counting object is asymptotically equal to 1 divided then by the number of progressions mod q that you consider times the total number of y smooth numbers that you allow. And what is important to us as well is that we get this result with a good error term, and good error term in this problem will always mean some 1 divided by a constant power log x. Just a few further words about the setup. And here y prime will always be of the shape fixed power of log x. And I think in this result, it actually works with a smaller choice than k prime equal to 1, but there are later results that we need where our k prime has to be sufficiently large and when we are away from being able to solve this, anything at the transition. Our choice of k is, our choice of y is always larger than the square of y prime. And we assume that y is also bounded below by a quantity of the shape fixed power of log x. And that exponent will also be sufficiently large. So it has to be sufficiently large with respect to k prime to start with. If you look at the setup here, one thing to note is that when you take the product over all primes less than y prime, if your k prime is larger than 1, then this product will be larger than n. And that means if you are going to study the set of y smooth numbers without small prime factors, it is not enough to study the set of y smooth numbers in arithmetic progressions. You have to do a bit more here. Okay. So with this result here, we have a candidate for an arithmetic function to which we can apply the methods, which would be the characteristic function of this set of y prime comma y smooth numbers. This characteristic function will satisfy the condition that it's equidistributed in progressions. How about equidistribution and short arithmetic progressions? A special case of this equidistribution and short arithmetic progressions would be equidistribution and short intervals. And in that direction, there is work by Delatortesh and Tenenbaum that we can use. In order to study equidistribution in short intervals, we would have to understand how this counting object changes. So how does the number of y-smooth numbers without small prime factors up to x, how does this quantity changes if we change the cut of x by a bit? So if we change this by a factor c, which is something between 1 and 2, then this quantity changes with some multiplicative correction factor, which is of the shape c to the minus alpha of x comma y. This quantity alpha that appears here is the saddle point attached to y smooth numbers below x. I don't need anything in this talk, any further information about this saddle point beyond that this is some quantity in our situation between 1/2 and 1, so a real number. And it does not change too quickly as we vary x a bit and as we vary y a bit. There is a result about how our counting object changes. And if you take this property into account, the most natural weight you can choose in order to obtain equidistribution in short intervals is to weight the characteristic function that we identified before by a factor of this form n to the 1 minus alpha, which will ensure that our new function is equidistributed, not just in arithmetic progressions, but also in short arithmetic progressions. If you take this function and restrict it to integers in a dyadic interval at scale n and normalize, then you arrive at this quantity. And if you would like to study solutions to linear equations, for instance, something like a plus b is equal to c, that will not be enough to have a function that is supported on a dyadic interval. And for that reason, we approximate this function by something that is defined for all integers n. The function g that is written here will be close to this function h on any dyadic interval where both of these functions are defined. This function g is the final object that we work with. That's the function for which we show that its centralized version is orthogonal to the sequences. Now we did a lot of work in order to produce something that is equidistributed in short arithmetic progressions. And why did we do this work? Well, there's some standard reduction that can be carried out, which reduces the problem of showing that a function is orthogonal to near sequences, to the problem where you have to show that the function, which no longer needs to be centralized, is orthogonal to what is called an equidistributed near sequence. The equidistribution, you can assume in this reduction statement here, depends on the error terms that you obtain in the statements about equidistribution and short arithmetic progressions. It depends on the error terms, it depends on how large you can choose the moduli in this equidistribution statement. And that is the point where our results do not match what you can prove for exponential sums any longer. So we obtain some function delta that tends to 0 as n tends to infinity. Equidistribution for near sequences says if you take these objects here and sum them over progressions that are not, these progressions live in the integers 1 up to n, they are not too short, where not too short is determined by this quantity delta, then you will find cancellation in these sums, and the quality of cancellation is also determined by this delta. And the delta will be much weaker than the delta you might have when you put in here an exponential sum with a polynomial phase function. Well, that is the problem. We would like to show that there's cancellation in these objects, and we would like to get this cancellation by making use of these equidistribution properties we may now assume on linear sequences. And for that reason, we would like to rewrite this expression into one where a direct sum over the linear sequence occurs, a direct sum so that we can put in the bounds we have here. And this you usually do by turning your problem, which is a one parameter problem right now, into a double sum, into a type 2 sum. There are lots of ways of doing so. For smooth numbers, there is an intrinsic way for rewriting a sum over smooth numbers into a bilinear sum. In Harper's work, such an intrinsic decomposition is used, but that decomposition is not efficient enough in order to apply in our situation when we would like this y to be fairly small. So we need a more efficient way of decomposing this sum. And this more efficient way can be achieved by using a result of Montgomery and Wang, which applies in a lot of generality. It says that whenever you have an arithmetic function f, you consider the sum over this arithmetic function over some subset of the integers 1 up to n, then you may bound this sum by a second moment that is weighted logarithmically, plus a bilinear sum that is also weighted logarithmically. And the bilinear sum von Mangold function occurs, and that is no surprise because this whole result is proved by introducing a logarithmic factor and then using the fact that the logarithm is the convolution of the O1 function and the von Mangold function. At least the proof is not very difficult, but the decomposition or the bound you get is extremely strong. When you apply this in order to study our program, when you apply this decomposition, to the sum which we would like to obtain cancellation for, then in our weight function.
That happens with somebody my age, doesn't understand. It's not usually a young person who knows what to do.
So our weight function g, if you restrict it to dyadic intervals, the weights that occur are essentially constant. And for that reason, when you try to bound these quantities here, you can remove the weights for that purpose. This second moment expression will be negligible, and one is left with studying these bilinear sums, these type 2 sums. And in our type 2 sums, we have one variable that runs essentially over primes between y prime and y, and a second variable that runs over y smooth numbers. And now what do we do with this expression in order to achieve cancellation? Well, we will swap summation. We will swap summation and we will restrict the n variable to a dyadic interval. And that reduces matters to bounding expressions of this shape. And now we have an inner sum that runs over a correlation of the von Mangold function with some object that comes from the original polynomial sequence that we were looking at. Now, it's known that the W-trig von Mangold function, when you centralize it, is orthogonal to near sequences. And this will be a near sequence, or is a near sequence. So you can replace this von Mangold function when you work with a W-trig by a constant function 1, and you will have here a direct sum over the near sequence. But that near sequence that occurs here is no longer the near sequence that we started out with. And we knew for the near sequence we started out with that when we sum it in progressions that are sufficiently long, we get cancellation. But in here, we are summing with this dilation by n. So it's no longer clear if there's still cancellation in the sums over this linear subsequence of the near sequence. So in order to finish the proof of our problem, we need to show that provided our original near sequence here is equidistributed for almost all little n's that are y smooth numbers without small prime factors and are in the didactic interval we are looking at, if for almost all such little n, this sequence here is still equidistributed, then we can solve the problem. I claim that is true And such results have been proved before, as for instance, it has been necessary to study this question, but without the smoothness condition involved in order to study correlations between multiplicative functions. And I'm sure that similar problems occurred in different contexts of applications of the nilport and Hardy-Littlewood method. However, the problem you run in here is that the set of n's we are looking at is extremely sparse, in particular when we would like this y to be a power of log n. So some of the methods that have previously been used in order to address such a problem are no longer available. What we do is to use some different methods and methods from before. So we use some result that occurs in Green and Tao's work, which is a generalized Lightman theorem, and it essentially translates equidistribution properties for nil sequences to properties of distribution of polynomials with values in R modulo Z. And then you further reduce to a question where you need to understand polynomial recurrence problems in R mod Z, which in this case are restricted to the sequence of y-smooth numbers we are looking at. We study that question using Fourier analysis and reduce everything to a bounds on Weyl sum, where the Weyl sums are restricted to our smooth variables. Such Weyl sums have been studied before in work by Drapeau and Shao, and we prove that their results can be extended to our subset of y-smooth numbers. Drapeau and Shao study y-smooth numbers, not y-smooth numbers without small prime factors. Once you apply these Weyl sum bounds, the bounds on the recurrence problems are still not good enough. So you need to combine those bounds here with a bootstrapping argument, and you have to run quite a number of iterations of that bootstrapping argument, and you combine that with good bounds on the distribution of our set of y-smooth numbers and progressions. There is quite a bit of work that goes into resolving this problem, but eventually you arrive at a resolution of it, and we arrive at a proof of the result I mentioned before, namely that we obtain in the almost optimum range for the smoothness parameter some function with support in the y-smooth numbers, more precisely with support in the y-smooth numbers without small prime factors, that has the property that when it's normalized correctly, the centralized function is orthogonal to the sequence. And that resolves the first part of what is needed in the Green-Tao machinery. What is still missing is a majorizing function in the general case. So we might ask at this stage what we can still do with this result, so long we don't have a majorizing function. If your smoothness parameter y is sufficiently close to the upper range here, so if you are in the dense or in a mildly sparse case, you can use a trivial majorand to work with. We are going to use a majorizing function that is the characteristic function of integers that have no small prime factor. That function can be used. It's been studied in a recent paper of Tao and Theorem, so we did not have to do any extra work here. In alternative to this kind of majorizing function, you can use a Sif majorand in order to remove small prime factors. A Sif majorand of the shape as it appears in Green and Tao's work, with the difference that the cutoff parameter for the primes you would like to remove is much smaller. Either of these two alternatives will have the property that when they are normalized correctly, then their centralized version will have small UK norms of all sufficiently large orders, and the so-called linear forms condition is available. And with these two pieces of information, you can deduce that the frequency with which such a system of linear polynomials takes values in our subset of the y-smooth numbers is of the expected size provided y is large enough so that the density of y smooth numbers up to n is larger than something like 5 times n. So this is a result in the sparse setting. It certainly goes beyond what was previously known in the dense setting. Nonetheless, it would be nice if one could go a little bit further. So one can improve on this logarithmic factor by working with some majorizing functions that work on a slightly longer interval and just working in the dense case here for the majorizing function. But are there other
Mildly
ways?
sparse means not log to a power.
Once again,
Mildly sparse.
mildly
means
sparse.
Not your case log to a power yet. In other
You
words,
want to replace this by some log n to a power? I think that might be possible.
Yeah.
But mildly sparse, I only mean that
Just that.
you are no longer in a dense space, and I don't care how sparse or how little sparse the set is. I just want something that is sparse. Okay, can we do anything else? When you work with smooth numbers, there's one very tempting approach, namely the set of y plus 1 smooth numbers trivially contains the set of y smooth numbers. Okay, so our majorizing functions have the properties that if you increase the y by 1, you get some majorizing. Our weight functions have this majorizing property. So it would be tempting to start in the dense case and remove one prime factor at a time. The Green-Tower methods cannot be combined with such an inductive approach, and I would like to explain this at the example of the inverse result for uniformity norms. A similar comment applies to any proof of the linear forms condition. So what happens in the inverse theorem? I will use a statement in the quantitative form, which is due to Manas, and I will use a transferred version as appears in the paper of Tower and Televeinen. What do we have? We have here a function f defined on the first n integers, which is majorized by a majorand mu, which is also defined on the first n integers. We assume that our function f is orthogonal to nil sequences. That means some converse statement of this here holds. For the majorizing function, we assume that it is small when centralized and the u 2 to the k norm. And then if f is orthogonal to nil sequences, we may deduce from this bound that f is small in the uk norm. Let's try and apply this with the majorand given by this weight function attached to y plus 1, and with f given by a centralized version of this weight function attached to y. So the data you have to put in is a bound on the u to the 2k norm, and you will get out a bound on the uk norm. And this drop in this difference in the exponent of the uk norm from 2k to k is not compatible with an inductive approach. If you look at the type of, at the quality of estimates you have to put in, there is an exponent c0 occurring in here, which is some number that is sufficiently large depending on k, and it is very definitely larger than 1. So you lose quite a bit. This bound here is quite a bit smaller than what you will get out in the end. And this polynomial dependence on the bounds is also not compatible with any inductive procedure. So this approach here is not going to work in the same way as SIF methods usually do not apply to smooth numbers. Okay, can we do nonetheless anything? Well, smooth numbers, if you weight the characteristic function logarithmically, you may decompose this characteristic function into a sum which runs over the primes you allow, and where you pick up a characteristic function of the divisibility condition that prime p divides n. If your integer little n is in a dyadic interval at scale n, and you may approximate this factor maybe by 1 divided by log n. And then if you look at the UK norm of our weight in a centralized version, you're looking at a norm. So this norm satisfies the triangle inequality, and this kind of decomposition allows you to bound above that expression you're looking at here by a sum over primes, where with some weights, the norms of our weight function minus 1 occurs, but no longer in the UK norm attached to the first n integers, but the range where you are looking at is now the integers up to n divided by p. And in this bound, the relationship between the summation range and the smoothness parameter is now much better than in the expression you would like to look at, because the closer y is to the cutoff, the denser the smooth numbers are that you are looking at. So you can use this kind of decomposition in order to still in some way inductively say something about the UK norms. And that will work on a much larger range than before. I hope it works on the full range, but that doesn't prove us. So we get UK norm bounds on a much, much larger range without inputting any majorizing function. And in a similar manner, you can count not general systems of, you can count the frequency of y smooth values in not general systems of linear polynomials, but you can count something that are hypercube-like configurations. These are configurations that are very close to the type of linear forms that occur in the Gauss norms. That means you start out with two vectors, one vector y0 and one vector y1. For any sequence of zeros and ones of length k, you define this vector y omega to take either the coordinates from here or the coordinates from there, depending on whether the exponent here is a 0 or 1. Then you are allowed to put in non-zero coefficients, and you are allowed to put in shifts. And then you arrive at linear forms that are essentially the linear forms as here in the UK norm expression, but with non-zero coefficients and with shifts. And for such expressions, you can get the correct order frequency count on the same range as you can get the UK norm bounds. And I would like to end with a problem, inspired by the investigation of what you can do so long you do not have a majorizing function. I would like to ask how a function looks like, if it exists, that has the property such that when you centralize it, the UK norms for all small k's are small. Mu f here is the mean value up to n. So you have small UK norms, but the count of 4-term arithmetic progressions for this function is not the expected count. So I would like to know if such a function exists, and if so, how it looks like. That would correspond to, normally, if you have a majorizing function that satisfies the linear forms condition, you know that this count of 4-term arithmetic progressions is controlled by the U3 norm. So if you assume that all these norms for all sufficiently large k are small, you should have the correct count of 4-term arithmetic progressions. I would like to know if a function, an easy function, exists that has small UK norms, but not the correct count of 4-term arithmetic progressions.
Any questions? Let me ask you a question. I asked Ben Green when he presented paper 2 of a series of 5 papers here, right in this room.
And you think if Ben Green could not answer this question, I could?
I can't remember his answer, you might. Since there's a guy called Leon Green, first proved the Ratner type theorem for null manifolds. It's quite effective and used representation theory of the Heisenberg group and so on. Has anybody ever used that viewpoint to get, rather than this sort of commutate, you know, the repeated commutator way of getting long pieces of orbit equidistributed, but rather harmonic analysis bounds, which the way you're presenting at the beginning, you had the linear part that you were saying can't extend, and maybe they're non-commutative. So the representation theory of the Heisenberg group is well understood. Has anybody used the exponential sums there? I guess it's a question for Liebman, but anyway.
So you want to know if you can get better equidistribution.
Yeah, maybe some special function.
That's what so is that kind of what you're missing? Yes.
Seemed to be what she was missing.
You're using the Green and Pau's equidistribution theorem for nil sequences. And if you had better equidistribution results for nil sequences, then you could adapt Harper's method maybe directly to.
It might work. I mean, there's a workaround, no? It takes a
The problem is with this arithmetic progression that you're stuck with, right? That you have no good bounds on the arithmetic progressions on which you have equidistribution. For which, when restricting to arithmetic progressions, you have equidistribution for the nil sequences.
Yes.
Your problem is there. So your problem is with that theorem.
Well, my main problem right now is that there is still a majorizing function missing in order to prove a result on the first.
That's for the second stage, but for the first stage, you're missing.
Yeah, but for the first stage, we obtain a result that is available on essentially the best possible range we can hope for. And Harper's methods, let's see. So Harper has a power 3 in there, and some other result.
But my question is, would
Maybe
anybody,
one can improve on what exponent.
I don't know if that's, you could try to do that.
no, I'm just
Try to
asking, has
work
nobody
with-
ever tried to use that?
I don't know.
I think it is very tempting on some of the results in the
But you could also try to examine if you understand bracket polynomial
Yeah, right.
distribution in some other way that
Yeah, right.
realizing it as a nil sequence.
Right. There are many ways to tackle it, but I like L2G mod gamma. So, and I think the first proof, maybe Molchev proved it first, but the history of the Ratner theorem in the null-puzzle case.
Maybe listening.
But Green did give a proof using the representation.
Yeah.
Leon Green.
Yeah.
Because I remember the discussion here was that Leon Green is not related to Bill.
Yes.
So I guess it would be nice if you had the same result where you were just dealing with y smooth numbers rather than y prime y smooth
Yes.
numbers. And you're introducing this restriction of y prime to avoid this issue about correlation and arithmetic progressions. And this is coming because genuinely your indicator function of smooth numbers is genuinely not terribly well approximated by a constant on these arithmetic progressions. But there's various other situations, at least, where you can approximate not by a constant, but by maybe some sum of terms involving lower order characters to take into account the fluctuations on arithmetic progressions. There's a few different ways you can do that. Have you thought about?
So I think there are results on understanding how large a typical y smooth factor of a I don't know z smooth number is, so that you understand the decomposition of a typical integer, and if you have a good understanding of these, say, anatomy of integer questions, then I think you can use our result in order to say something about the original question where you have just y smooth numbers. And I haven't thought about this very carefully. In the end, I decided y smooth numbers without small prime factors are sparse subsets.
Yeah,
And
sure.
the y smooth numbers, so in some way, I solved my problem.
Yeah, because in some way you're
I think
taking a
it's a bit
major arc
unlikely.
approximation, and here you're taking the most major arc that there is, which is just the tiny arc around 0, which is y approximated by mean value. But you
So I
take-
believe it should be possible to put these y prime smooth.
And yeah, you can certainly
complement
count
again, but
sort of small arithmetic progressions over the sets that you're looking at.
yeah, I haven't seriously tried, but I believe. Yes.
Suppose you have this majorizing function.
Yep.
Then does it follow automatically from the methods that within, say, subsets of the y smooth numbers with positive relative density, you can find arithmetic progressions?
Progressions. Once you have those majorants, then the relative similarity theorem that's proved in Green and Tao's paper applies,
Okay.
provided you have your majorizing.
Applications, I do have a suggestion to one.
Okay.
There's a Linux observe that you can show that the set of characters which agree on the first few primes statistically and conductor Q is very small. So if you assume Riemann, then if you know the first log conductor squared values of a character or of an automorphic form, then it's determined.
Okay.
But you try to prove that the set of such automorphic forms which have a small initial segment with the same values is very small. And Linux used sieve methods and smooth numbers to give upper bounds like this. And it seems to me you could open that door quite a lot. There's a very, very nice paper of Duke and Kowalski, which does this for automorphic forms. And this seems to allow you maybe to go to elliptic curves where you would have all sorts of side conditions
Okay.
with upper bounds. I mean, maybe you have other applications, but this looks to me ready for such multiplicity bounds. Yeah.
Okay, any other questions? If not, let's continue again. Thank you.